All right, cool. It's time for our last talk of the day. I have a few quick announcements. Probably to Hugo's chagrin, I actually made it through an entire day without speaking about parties, but there's another party tonight. For those who have not attended Recon, we usually have 2 every year. Tonight, it's described on page 12 of your guide. We'll be going to Catacombs, which is about the same distance as the venue last night. Maybe you're like me and you forgot about how you felt when you woke up this morning, which is great because we have another open bar tonight. There'll be DJs, it'll be a lot of fun. And now for our next talk. This is Bill, it's his first conference talk. He's had a really interesting day, which I'm gonna leave it to him to tell you about.
Yep. So when I was actually walking over here, I got hit by a car. So I've been in the hospital for a few hours, but now I think I'm good, ready to give this talk. I'm excited. So my talk's about the unseen dangers of bloatware. I'm 17 years old. I love breaking stuff. I graduated high school about a month ago, and I'm a software engineering intern at CrowdStrike, and I'll be attending Rochester Institute of Technology next year. So what's this talk about? It's widely known that bloatware already slows down your computer, and it takes up unnecessary space. But in this talk, I want to talk about another risk, the potential security risk. And I want to show why leaving bloatware on your system is definitely not a good idea, not just because of performance or storage, but because it could lead you open to security vulnerabilities. And the vendors I'll be talking about in this talk are Dell and Lenovo. So the vulnerabilities in this talk are 1, remote code execution in DellSupportAssist, local privilege escalation in DellSupportAssist, cross-site request forgery in Lenovo ServiceBridge, and remote code execution in Lenovo ServiceBridge. So, DellSupportAssist, that's a great piece of software. It's advertised to proactively check the health of your system's hardware and software. It unfortunately comes pre-installed on most of all new Dell machines running Windows, which means if you have a Dell computer, you probably have it. It provides a convenient online interface to update drivers and miscellaneous software. One of the larger concerns is that, since it's pre-installed, a lot of endpoints run this software. So what got me looking at Dell is, back in September, I actually got this computer right here, and it came with a terrible 1 terabyte hard drive. I wanted to upgrade it to an SSD, and so part of that was reinstalling Windows. When I reinstalled Windows, I had to go download drivers, and I went to Dell support page to see what I could find. When I went there, I saw this detect PC button. That was very suspicious. How could a website detect my PC? So when I clicked on the button, it just presented me with this, you need support assist. What you get? It told me that I could automatically update all my drivers for me, and it provided long-term support. It was sounding pretty good to me, but as I looked into it, it turned out that actually on my old hard drive, this was already installed. So when I first opened it up and I started network logging in Chrome, I found that it has a persistent connection to port 8884 on my local computer. This meant that the service running on my computer actually opened a port. And it would provide a signature and expires parameter, which hinted at an authentication system. And it kind of seemed redundant because all the signatures and expires tokens were available on a website that Dell exposed, so I'm not sure how much security that provided. So when I found an update that I needed to install, I pressed the download button, and I found that first Dell will make a post request containing the details for the update. It'll make the request to the download service API, which is specified in the URL, and it'll query the download service for a status update on how the download is going. The post request has some concerning data like location and path. What I mean by this, for example, the location specified the download URL, where it was going to download the update from. And it seemed kind of weird that Dell would even trust this much user input. For example, later on when I looked at Intel driver and support assist, they take in a driver ID, no download URLs, no paths, and it'll actually resolve the download URL by itself, which is much safer than accepting just straight up user input to download. So the service was programmed in C#, meaning that I could pretty much open it and decompile it pretty easily in dnspy. So I found out where their web server was initialized, and what happened is it'll usually start on port 8884, but this depends on whether it's available or not. So before starting the thread for the web server, it'll query the active physical session using WTS getActiveConsole_session_ID. It'll grab the token of this session and attempt to find an elevated token that is linked. Finally, it'll start the thread for the web server while impersonating this token. So before your download request is actually processed, there are several integrity checks that Dell put in place. The first check ensures that the request is from the local machine. They do this by checking the request destination and making sure that's a loopback IP address. The second check ensures that the refer header in the request is from a whitelisted host. The third check ensures that the signature parameter is a valid cryptographic signature of the request to the API method. I tried bypassing the first check using Ethernet and spoofing packets with SCAPI, though that didn't get far. Even if I did bypass the first check, anyone with Windows Firewall enabled would be safe, as there's no incoming rule for the web server port. So if you pass these checks, the next step is dispatching your API request. There's a method called callServiceMethod, which is responsible for finding the function to call. Give it an API name. So for download and auto install, the request is sent to a class called download_service_logic, where the data you provided in the post request is deserialized and verified. The fourth check makes sure that the download URL does not start with http://. If it does, it'll use C# string replace method and replace all instances of http:// with https://. The idea behind this check was to make sure that a download URL wasn't made with an HTTP as a protocol, so that someone couldn't ARP or DNS spoof it. The fifth check makes sure that the download URL is actually a Dell download server, meaning I couldn't just provide my own website to download from. If you pass all these checks, the specified file is downloaded using a simple C# HTTP web request. The final step is to actually execute your program. The agent does this by using a named method called launchProcess and readSTD output. This method will call onto command prompt to start the downloaded program. So to review what Dell does, they'll first make sure the request is from the local machine. They'll make sure that it has a whitelisted refer header. They'll make sure that it has a valid signature and expires parameter. They'll make sure that if our download URL does start with http://, they'll filter it out. And then they'll make sure that our download URL actually is a whitelisted host. So all of these checks can be circumvented. So the first localhost check can be bypassed by making the request from a web page, because it still appears that your web browser is making the request, which is on the local machine. The second refer check can be bypassed by making the request from a whitelisted host, but that we connect to using the HTTP protocol. What I'm thinking about here is that we can use ARP and DNS spoofing to actually have it go to our own servers. And so we could provide JavaScript payload to exploit the system. The third signature check can be bypassed by just grabbing the signatures from Dell's webpage. There's not really much to it there. The fourth check about the download URL containing http:// can be circumvented by having our URL start with space http:// http:// or all caps http://. There's just so many ways, because what they do is just check, does the string start with http://? It's not a very secure check. And then the final check is just pretty simple, because, I mean, if we can provide an HTTP URL to download from, we can just spoof the packet and give it any payload we want. So using all these exploits for these different checks, we can actually achieve remote code execution. So here we have a demo. Okay. Not sure is it going to start or not. It's concerning, to say the least. We can probably open it up manually if it doesn't want to start on us. All right, great. Technical difficulties, first talk. This is great. This is great. I love seeing this. Okay, it doesn't really want to start. Okay, let's quickly see. Not sure if you're going to be able to see this, but are you able to switch to my screen HDMI at all? No? Okay, let's see if we can actually open that up. Okay, it duplicated my display. Is it coming up? Oh, yes, it is. Okay, great. Oh, okay. So, let's just step through this real quick. So, first of all, you just start my exploit proof of concept, just running it straight. You provide a interface to use to actually spoof. You provide the router IP address and a target IP address, and you provide a payload path to deliver to the victim. So you see here, I just have ARP spoof and DNS spoofing. It's pretty straightforward. I use SCAPI for most of this. So on the victim's machine, all they do is visit a page that has our malicious JavaScript in it. I don't know if you guys can see it, but on the bottom left, we see that it's making a request to dellrce.dell.com. That's where our payload is. The attacker receives confirmation that the exploit is in progress. You can see exploit binary requested. That's the key thing. That means that the SupportAssist agent actually downloaded the exploit. Then, finally, receive remote code execution. And in this case, the malicious payload is calculator, which we all know is very terrible. You don't want that running on your system. So yeah, that's the remote code execution vulnerability. Okay, that works. So can you find out what's wrong with these pictures here? So this is for the next vulnerability, by the way. On the left, we have a process called SupportAssist_AppWire.exe. It's an unelevated process. Except in the middle, we see that it has a full control thread handle to a process called SupportAssistAgent.exe. And on the right, we see that the SupportAssistAgent.exe is running as anti-authority system. Hope you guys maybe figured out. Basically, an unelevated process has a full control thread handle to a system process. That's not that good. So let's see why this happens. So 14 days after you first launch DellSupportAssist, it'll start showing these convenient, optimized system notifications on a daily basis. So it just says, run SupportAssist now to ensure your PC is up to date and running at its best. Okay. I definitely did not run it. So this notification is actually created by a process called SupportAssistAppWire.exe, the one we saw on the last slide. And that process is actually started by a method called launchUWPApp. LaunchUWPApp takes in an application name and arguments to launch the application within its parameters. Next up, it'll iterate all Explorer processes and try to grab its token. It'll make sure to grab the link token that's elevated, but still Explorer runs as unelevated on Windows machines, so it's basically grabbing an unelevated token. And finally, it'll actually start the application using create process as user. Pass.
Can you take the mic on the table? Just to your left.
Oh wait, it doesn't work? Yeah, it works. Okay, no problem. It's fixed. Okay. Great, guys. Great. Please put up. Okay. Hello. Okay. It's just, I think the sensitivity is messed up a little bit, but we can deal with this. I'll just talk a little louder, hopefully. Okay. So, it'll start the application using create process as user. All right, this sucks. Yeah, I'm this one. Okay. Okay. Is this one on? Oh, all right, now it's on. Okay, so it'll start this process using create process as user. And so the issue here is that we see that it passes on some pretty standard arguments, but then we see that it set B inherit handles to true. So basically what's going on here is that the SupportAssist agent, which is running as a system process, is starting this child process while giving it all inheritable handles. Now the issue is this child process is unelevated. So it basically gets a threat handle because that one is set to be inheritable. That's not that good. So let's see how we can exploit this. The easiest way is just to use QA user ABC. It's called load library, but there are some tricky requirements we have to get past. First, load library takes in a parameter for a buffer, the DLL name buffer. So we're going to need to have some way of providing a DLL we can access. And the second way is we need to find a way to actually trigger the APC. You know, we have to find a way to set the thread to alertable so that the APCs are processed. It turned out load library doesn't really care if you have a binary extension. You could use any extension and it didn't care. It would load it would load it as a library. So this meant that all we needed to do was find a buffer to a file path we could access. So I used Process Hacker for this, and I went into their strings utility to try to find any instances of any strings that are in the R data section of any loaded module. And that contains C:\\. And so when I searched for this, I was kind of shocked at the first result. We see here it's just C dev SQLite core SQLite3.pdb, but the address starts with 0x180. That's pretty scary. So I looked into the modules list of the process, and I sorted by base address. The first one I saw is SQLite3.dll with a base address of 0x180000000. So was ASLR disabled? And it turned out when I opened up the DLL and CFF Explorer, it was missing the dynamic base characteristic, which means that ASLR is disabled for that module. And so when I restarted the process and even updated the agent, at the same address was a string cdev SQLite core SQLite3.pdb. So this meant we had a predictable base location where we could actually use it and we could write to it. We could write our exploit payload to it. And now we know where the buffer is too. So the next issue was actually trying to find out how we can set the thread to an alertable state. So looking at the stack frame for this thread, I found out that it was actually the service control handler. So if we could trigger the service control handler, we could escape the little wait it has waiting for a next service control signal. So looking into the permissions of the service, I found out that interactive users could actually interrogate the service, meaning the service control handler would receive an interrogate request, and it would get it out of its little, wait for the next service message loop. And then, so to actually execute our APC, to set the thread to alertable state, we can use set thread context. To set the thread, to the RIP register to anti-test alert, which will immediately just empty any APCs and actually execute them. It took no parameters, so this was actually pretty easy to do. Okay, let's see if this video works. Okay, it's not great, but okay. We can go quickly. Let me quickly just make sure I don't accidentally reveal anything, any secrets. Yeah, okay, found it. Okay. Oh, no, don't show them. Okay. All right. So the exploit starts out with when we receive this optimized system notification in the bottom right, the one I was talking about. This indicates that SupportAssist AppWire actually executed. So the next step is to actually run the exploit. And you see it goes very fast. But in this CMD that's executed, you can see that we're actually a system. So let's see just the output log of my little program to see what it did. So it starts out with the top process here, if you can see my cursor, right here. Yep, okay. So it searches for this SupportAssist AppWire binary. And then once it finds the binary, it'll create the PDB folder file chain, you know, from C, Dev, SQLite into the PDB file, and it'll actually write our DLL. And then it'll create a child process, which will again search for SupportAssist AppWire down here. It'll then try to find the thread handle that was inherited. And then it'll first queue the APC to load library our malicious DLL. And then it'll open up the service manager to send the interrogate message. And it will first suspend a thread, then set thread context to anti-test alert. So after all that, your system shell is launched, or whatever program you want. My DLL just launched a system shell. And there you go, that's how you get local privilege escalation. Okay, so when I was looking into DellSupportAssist, there was also some privacy concerns I had. I felt that at some points it was being even invasive. And so what I found was, for example, on most exceptions, the agent will send the exception detail along with your service tag to Dell servers. Okay, not that bad. Whenever a file is executed using download and auto install, Dell will send a file name, your service tag, the status of the installer, and the logs for that install to their servers. Okay, sure. So whenever you scan for driver updates, any updates found will be sent to Dell servers along your service tag. All right, we're getting a little bit, weird here. And then whenever Dell retrieves scan results about your BIOS, PNP drivers, installed programs, and operating system information, all of it is uploaded to Dell servers. Every week, your entire log directory for this SupportAssist agent is uploaded to Dell servers. Every 2 weeks, Dell sends a heartbeat, including your device details, alerts, software scans, driver scans, basically everything about your system. You can disable some of this using privacy controls, but the scary part is that this is enabled by default, meaning there's probably millions of endpoints out there who might not even be aware that they're running Dell SupportAssist, but they'll be transmitting data constantly. I don't know about you, but that's pretty scary to me. So the next product I'll look into is Lenovo ServiceBridge. Lenovo ServiceBridge is designed to help with updating and with any hardware trouble you have on your computer. It's advertised to automatically detect your machine's serial number, machine type, and model. It can download multiple files at once from the product's download section. Unlike Dell SupportAssist, Lenovo ServiceBridge is only installed when you go to update your system using their utility. Confuser X version 1. So after loading the application, I've seen this used before. Again, but I could never imagine it being used for corporate caught off guard. It's kind of because I saw this confused by attribute. What were they trying to hide? Confuser X version 1. Now I've seen this. Used before, but I could never imagine. it being used for corporate products. It's kind of scary. What were they trying to hide? So, anyways, deobfuscating wasn't a big deal. Confuser X version 1 is pretty old, and there's a bunch of deobfuscators already out there. So you just pop it in, and it gives you a brand new module that you can open up in DNSpy and see everything with. So when the application first starts, similar to DellSupportAssist, Lenovo ServiceBridge starts an HTTP listener, typically on port 50128. When the HTTP listener receives a request, the software begins by ensuring the refer header starts with a whitelisted host. The request handler exposes several API methods, and the one that caught my eyes was one called OS-Diag. I went through each API method, and I was just trying to find anything that looked suspicious. And this one was pretty suspicious. And so you're only supposed to be able to make requests from a few whitelisted domains. They do a refer check. What they do is they'll make sure the refer starts with a whitelisted host. So the API, OS-Diag, will first start off by checking whether or not local app data Lenovo ServiceBridge OS-Diag temp file .diagcab exists. If it does, it'll go ahead and delete it. The API then instantiates a .NET web client and downloads the URL straight up. And it'll actually, the download URL specified in the request post data, and it'll actually save it as a diagcab file. After the download has completed, it'll go ahead and actually just straight up start this diagcab with absolutely no verification. So looking back at the checks we need to pass to call OS-Diag, we must first have a refer header start with a whitelisted host. For example, the URL pcsupport.lenovo.com.build.DemirKapi, my name, .me, will actually be considered a valid refer. Lenovo did not implement a check on the URL passing for OS-Diag. So if you can bypass the refer header, you can arbitrarily execute any diagcab file you want. And diagcabs do need to be cryptographically signed, but I've seen several instances before where they've been used maliciously. Okay, so let's try to pull this off just because one's gonna work. Probably not. Okay. Let's go try to find this now. Okay. So, first of all, the victim has to visit a URL. In this case, this is my URL here, rc.html. And it'll tell you even how long it takes to exploit. Then, the exploit is done. It's pretty simple. A diagcab pops up. And you can control, the description. You can say, your computer's about to die. You need to update. You need to fix something. There is user interaction required, but it feels like if I saw something like this, and I was an average user with no security background, and I had pretty convincing maybe icon, add a Lenovo icon, or add a convincing title or description, I might click on it. And so in this proof of concept, all it does is it just starts up a command prompt. So how diagcabs work is you can give it a PowerShell script to execute, and in my case, I just made like a one-line PowerShell script to start up a command prompt. But it's pretty dangerous because you can have the PowerShell really do anything. And this is also completely remote. In the DellSupportAssist remote code execution, I would have to be on your network, and I would have to ARP and DNS spoof you. But with this, all you need to do is be running Lenovo ServiceBridge and visit a web page, or even a hidden iframe. So it was, in my opinion, it was pretty dangerous. So Lenovo also had some privacy concerns. I didn't just want to leave Dell out there, But so with every request, Lenovo pretty much sends basic details about the current user and basic details about the system. Nothing is anonymized, just like DellSupportAssist. So when this web server starts, Lenovo sends details about the port. On most exceptions, Lenovo sends details about the code that caused the exception. And with most API methods, it'll just tell their server, oh, this client here executed this API method. Here's their details. So the disclosure process. How did Dell and Lenovo perform when it came to patching vulnerabilities? Dell took 6 months to address a remote code execution vulnerability. For the local privilege escalation vulnerability, they only took a month. So between those two, they got significantly better. But when we take a look at Lenovo, they took 2 weeks to fix a remote code execution vulnerability. So, yeah. So before I end this talk, I want to give some thanks to Alex Ionescu. He should be in the room. He told me he was going to watch me. Were you, Alex? Okay. All right. I hope you didn't lie to me. Whatever. And so without his knowledge about Windows internals, there's no way I could have found these exploits. So he was definitely a big help. And on the Dell side, Rick Martinez, which I see him sitting right there. Hi, Rick. Thank you for your help for coordinating with Dell. I definitely appreciate it. You know, he made the process a lot easier. And Dell was much more cooperative with me because of him. So this is my contact details. I'll be publishing a write-up soon, probably in a few days. Let my back heal for a bit. You know, just make getting hit by cars is definitely not fun. And if anyone has any questions, I'd be happy to take it.
Hey, Bill.
Hey,
so
Alex.
Do you think that it was Dell or Lenovo that sent the car that hit you?
Not sure, man. It was Dell.
Great presentation, thank you. I was curious with the, I think it was the Dell software where the system process, the support agent spawns the child process and it set inherit handles true.
Yep.
Did you get any sense of why that was done? Like, did they have a reason for it?
No. I think it just developer left it set to true, probably wasn't thinking much at the time. Maybe they didn't realize Explorer was unelevated usually.
Okay.
Have you taken a look at the patches?
Yes. They set inherit handles to false.
Yeah, that was
Okay. Anyways, thank you for coming out. I appreciate it. Good first talk. Good first talk.